Now we're going to focus on a zone called the platform assembly stage and show just the relative components. Here there may be several subassemblies that make up this section. Trying to assign any particular designer under this scheme is nearly impossible. Zones enable design management from a graphical method as opposed to a file method. Next we're going to add some more equipment like robotic arms into this assembly. Notice this subassembly contains some predefined assembly relationships for placement. This has been captured with a component as these relationships are always needed when adding it into a new assembly. For this last relationship, we'll create a planar offset from the end of the platform of 0.75 meters. After placing the first robotic arm, we'll again use the component move command to replicate this arm across the platform. In this case, we're going to maintain the relationships within the select set. In the move options, you can see we have an option to move and to copy. This is the options we're going to use. We're going to go from a key point, and then we're going to use the get point option to actually get the coordinates of that corner on the platform. That gives us the x, y, and z coordinates, and we simply want to add 1 meter to the y coordinate to replicate this 1 meter back. In the command bar, we also have an option to repeat, which will add another meter and add yet another robotic arm. Trying to manage all these various systems under a single subassembly would be nearly impossible to do. But with zones, any newly added components will be added to that zone automatically, which means that the designer's zone will always be kept up to date even when parts are placed by others. Also, when that designer opens the assembly, he or she can open it with just that zone being loaded into the system memory. Obviously, there's great performance gains with this unique capability. Next, we're going to create a mirror plane because these robotic arms need to also be placed on the opposite side of the platform. So we're going to create a mid-plane to mirror about. So let's mirror the first three about that center datum plane, and since there isn't any convenient face, we've created that plane based in the middle of the existing part. So mirroring a part can result in three conditions. We can mirror the geometry about the plane, like the exact mirror of the suspension components on a car, left hand and right hand, or we can simply rotate parts, and this is how we can handle things like nuts and bolts, or we can omit them from the operation completely. Solid Edge gives us all of these options, and no matter what we need, we can accomplish it. In this case, we just simply need to rotate the robotic arms into position on the opposite side. So in this dialog box, we'll change the action for each one of these from mirror to rotate, and we want to mirror and we want to rotate about the front plane. As you can imagine, all of these robots need to perform different operations. Note that the robot subassemblies are simply instances of that same subassembly, and so by moving one, we don't want to adjust the position of all of the others. We can simulate the operation of just one of the robotic arms independently by making it an adjustable assembly. If we move this robot, just this one robot, the others will stay put. In cases where you're wondering, since there are 6 robotic arms, the quantity in the bill of materials will stay at 6. During a drag move of the assembly, we can drag free along the vectors defined by the part geometry, or we can key in explicit values. All of these options are conveniently listed on the command bar found along the left side of the screen. To show some more examples of the power of zones, we're going to pose as the engineering manager reviewing the progress of this plant. What progress has been made on the quality assurance room? So we'll just turn on that zone and find out. Remember that zones automatically pick up any geometry added to that geographical location, even from a different designer. Solid Edge provides the best tools for manipulating our design data. We can show only what is selected in an edge bar, we can find small parts, we can show a range box of parts, we can select similar parts, or like here, we can turn on everything to check our progress. We saw earlier the ability to replicate parts with a copy command, but Solid Edge also has some very sophisticated patterning tools. You may remember doing the patterning in the 2D, but those same powerful patterning capabilities are available here in the 3D. While simply patterning components along X or Y may not be overly impressive, as seen here by just adding the 2 additional conveyor stations, watch what happens when the pattern needs to extend across the shop floor. We have a pattern sketch that defines where the end of the conveyor run extends relative to the door opening. So with that in mind, we're going to change a variable that drives the location of the door in the wall. We'll do that through the variable table. So let's blindly change the value of the variable that defines the distance to say 30 meters. The lead engineer has apparently set some limits to what the value can be based on the building size, or possibly a building code or structural limitation. So as the layout engineer, we didn't necessarily know that, but Solid Edge does and rejects that value. Notice that we have a range of values that is acceptable. So in this case, we're going to set that to 22. Limits are a perfect way to ensure key dimensions are being manipulated. The same level of error checking happens should the attempt to modify the dimension directly. Now you see the pattern update to the correct length needed to reach the door opening. Reuse and use of simple 2D layouts from a plant designer or architect can be effortlessly imported into an assembly to initiate plant layout development. Solid Edge builds upon a governing 2D layout with a unique 0D workflow that lets us capture ideas and requirements quickly and during the concept and plant layout planning phase. Ensuring all of our data can be leveraged, Solid Edge's approach to plant equipment layout and design can utilize a mix of 2D, virtual components, super light virtual real components, and 3D parts and subassemblies. Solid Edge is built on a sound architecture where commands and workflows are optimized to maintain performance without sacrificing quality or usability.